أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم.
In this session, we are going to look into how to use SmartPLS 4 to run binary logistic regression. Now what I will do is I'll click new project and let's say I name it binary logistic regression. Create. The first thing, let's import our data file. Here is my data file. This all looks perfectly fine. Let's import it. Now just double check that if everything is fine here. The minimum, the maximum values, the mean values, the type of these variables. Go back, create your model. Now in this case, I'm interested in a regression model, not the PLS SCM model, not the process, not the CBSCM, just plain simple regression. And let me name it logistic regression and save it. Now here is my canvas and here are my variables. Now my dependent variable is choice and these are my predictors. Now before I go on and do the model here, I will brief about what is binary logistic regression, the example that we are taking into account and how, and then we will run the model followed by the interpretation of the results. Binary logistic regression analysis using SmartPLS 4. The concept of binary logistic regression. Now, regression technique is used to assess the strength of a relationship between one dependent and independent variable or variables. It helps in predicting the value of a dependent variable from one or more independent variables. Now, regression analysis helps in predicting how much variance or change is being accounted for in a single response, that is dependent variable, by a set of independent variables. Now, linear regression analysis requires the outcome criterion variable to be measured as a continuous variable. This is what we have seen in our last session as well, where we looked into how we can use regression analysis to predict an outcome that is continuous. However, you may encounter situations where you would like to predict an outcome that is dichotomous or binary. Now, in such a situation, a scholar will use binary logistic regression to assess the impact of one or more predictor variables on the outcomes. Now, logistic regression analysis is a method to determine the reason-result relationship of independent variable or variables with a dependent variable. Now, what it does is it predicts the group membership based on one or more predictors. Now, since logistic regression calculates the probability of success over the probability of failure, the results of the analysis are in the form of odds ratio. And we will look into this as to what odds ratio mean. Logistic regression determines the impact of multiple independent variables presented simultaneously to predict membership of one or other of the two dependent variable categories. In logistic regression, the expected outcome is represented by 1 while the other is coded as 0. Now, what are the example scenarios? A scholar may utilize binary logistic regression in following situations. A store would like to assess factors that lead to return or no return of customer. Now, whether the customer will fall into the return category or no return category. Based on certain factors, you can calculate this, assess this, analyze this based on binary logistic regression. A college would like to assess admission, that is, whether to admit or not to admit a student based on their age, grade, aptitude test results. Now, what you are doing is you are assigning a particular category to a student, whether it will be or whether the student will be admitted or not admitted. Now, a scholar would like to predict the choice of bank. whether public or private. Now, whether I as a respondent in a study will choose public sector bank or a private sector bank, this may depend on the use of technology, the interest rates, the value-added services, the perceived risk, reputation, and other variables. Now, all these examples or all these situations are analyzed based on binary logistic regression. Now, the example in this particular session is the last one, where we are predicting the choice of bank. Now, there are a few assumptions. Logistic regression does not assume a linear relationship between the dependent and independent variable. The independent variables need not to be on interval nor normally distributed, and you do not need a linear relationship as well, nor you need equal variance within each groups. Now, the error terms or residuals do not need to be normally distributed. The dependent variable must be dichotomous with two categories. Now, this is binary logistic regression. Now, the categories groups as a dependent variable must be mutually exclusive and exhaustive. A case can only be in one group, and every case must be a member of one of the groups. Large samples are needed then for linear regression. A minimum of 50 cases per predictor is recommended by field. Or LeBlanc and Fitzgerald suggested a minimum of 30 observations per independent variable. Now, here is the example for this particular session where we've got these variables and I want to predict the preferred choice of bank based on these predictors. Now, whether based on these predictors, a respondent will choose public or private bank. Now, the dependent variable encoding table shows the coding for the criterion variable. In this case, those who will choose private sector banks are classified as 1, and those that will not choose private sector banks are classified as 0. Now, the preferred choice is 1 and the other is 0. So in this case, the dependent variable is preferred choice of bank, that is choice variable, and the preferred is 1. Private sector banks classified as 1. Now, how do we run logistic regression or binary logistic regression in SmartPLS? Now, we've got this canvas. I've got this dependent variable, so I'm going to click on it, drag it, and drop it here. Now, here is my dependent variable choice. I'll click on it and move it here, let's say in the center. And all these other variables are my predictor variables, so I'm going to select all of them. What I did was I just clicked on one, the shift button, down arrow, and I selected all on these, drag them and drop them onto this dependent variable choice. Now, here are all your predictors and this is your outcome. Okay, we can slightly arrange them. Let's say I'll put them here. Let's say I'll put this one here, and there's one other one. Let's say I'll put them here. Now, make sure you save it. Now we are ready to run the model. Calculate logistic regression. Click on it. And let's use the default settings and press start. Now, here are your results, and these are your coefficients. This is your R square. In this case, they have mentioned the McFadden R square value. You can change it to Nagelkerke R square, which we are going to use in this study. Now, here are your path coefficients. This is your intercept. Now, how do we understand? What do we get out of this logistic regression? What are these numbers? Now, there are different results here. Your path coefficients. Now, this one has a significant impact. 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 The rest of them are insignificant in leading to or selection of choice, whether one should use private, or whether one will use a private sector bank or a public sector bank. Now, the model fit statistics. Now, if you want to export it, right click, export as image. You can do it as external file or clipboard. Now, how do we interpret these results? So let's come back here and look at the model fit statistics first. And where are these statistics here? These are here. So what I've done is I've divided this table here into multiple smaller tables in order to develop a better understanding of the output. You can copy it into Excel or Word and just simply paste it there. So what do we mean by this log likelihood and deviance for the null model? Null model is one without any predictors. So you've got a model, but you do not have any predictors in it. And then the estimated model, the one with the predictors and the outcome. So how well the model, or whether there is an improvement in comparison to the null model when you are estimating the model. So if there is an improvement, this means that the model fit is good or it is acceptable. Now, how do we interpret it? Let's do that. Now, here are our results. Log likelihood. Log likelihood is the natural logarithm of the likelihood function. In logistic regression, it represents the logarithm of the likelihood that the model would generate the observed data given the parameter estimates. Now, what it does is it estimates whether there has been an improvement in the model from the one with no predictors to the one that has predictors. Now, if you look here, the log likelihood is minus 196.800 for the model with no predictors at all. And the one that has predictors has log likelihood minus 176.402. Now, higher values of log likelihood, in this case, we can say alternatively, the smaller negative log likelihood indicate a better fit. Now, in this case, the model with predictors has a smaller negative value. This means that the model is a good fit. There is a significant improvement from the null to the estimated model. Now, the other model fit statistic is deviance. Now, deviance is a measure of how well the model fits the data, similar to the residual sum of squares in linear regression. It is calculated by comparing the model's likelihood to the likelihood of a saturated model, a model with a separate parameter for each data point. Now, this is too technical. We do not need to get into detail as to what it means or how it is calculated. Now, in our case, we need to understand that lower values of deviance indicate a better fit of the model of the data. Now, for the null model, deviance was higher. With the estimated model, the deviance is lower. Now, in this case, the estimated model does fit well. Moving on. Now, in the same model fit table, we've got R-square values. Now, there are different R-square values. Let's have a look. We've got these: Cox and Snell R-square, Nagel-Kirke R-square, McFadden R-square. Now, in this case, I'm using Nagel-Kirke R-square. Model summary shows the pseudo R-square. Now, this is your pseudo R-square. Now, pseudo means that it is not technically explaining the variation, but they can be used as approximate variation in the criterion variable. Normally used the Nagel-Kirke R-square. This is an adjusted version of Cox and Snell R-square that adjusts the scale of the statistic to cover the full range from 0 to 1. Now, in this case, the value is 0.165. If you convert it into percentages, it would be 16.5% change in the criterion variable can be accounted by the predictors in the model. Moving on, then we've got other statistics as well. We've got AIC and BIC. Now, AIC is a measure of relative quality of statistical model for the given set of data. Now, lower values of AIC indicate a better balance between model fit and complexity. For the null model, we had 395.601, and for the estimated model, it was lower, that is 374.805. Now, if you see here, BIC is similar to AIC but penalizes a more complex model. Now in this case, we do have a complex model. We've got multiple predictors predicting the outcome. Now that is a possible reason that you've got higher BIC for the estimated model in comparison to BIC, but all other fit statistics are good, so we can say that our data fits the model well. Now, the model fit details provide insights into the goodness of fit and performance of the logistic regression model. Now, lower values of deviance AIC, not the BIC, as well as higher values of R square indicate a better fit of the model. Now, whether you should use AIC or BIC, if you have got and you are looking for prioritizing model fit over simplicity, that you've got a complex model, then you should use AIC. If you've got a simpler model, then you can use BIC. Now, in summary, if you prioritize model fit and are willing to accept some level of complexity, use AIC. If you prioritize model simplicity, you've got a simple model and want to avoid overfitting. Overfitting happens when a model becomes too complex. Then you should use BIC. For simpler models with limited number of predictors, use BIC. Otherwise, you can use AIC. I would still encourage you to read more on both these concepts. Now, there is one other table that you get from SPSS. In SPSS, when you get it, you refer to it as classification table. In logistic regression, in SmartPLS, you get it as confusion matrix. Now, what does this table mean and where is this table in the results? Now, if you click here, prediction and probabilities, and click here, confusion matrix, you will have this classification table. Now, what does this mean? Now, the objective of the confusion or classification table is to evaluate the performance of a classification model, such as the logistic regression. Now, when the actual value is 0, this is the actual value. The model predicted it as 0 in 61 instances. Now, the correct prediction when your actual choice or observed choice is 0 is 61. And incorrectly in 29 instances. So when the observed choice was 0, the model incorrectly predicted it in 29 instances. So the correct percentage was 67.778. Now when the actual value is 1, that is the preferred choice of private sector banks being selected, the model predicted it as 1 in 159 instances. That is the correct prediction. So when the observed choice was 1, the correct prediction by the model was 159 times or instances, whereas the incorrect prediction was 92 times, that is 92 instances. In this case, the correct percentage was 63.347. So in both cases, whether you were predicting the choice 0 or choice 1, most of the times the prediction was correct. Look at this, 61 is greater than 29, 159 is greater than 92. Now again, the classification table provides an indication how well the model is able to predict the correct category once the predictors are added into the study. Now, the model correctly classified 64.51% of the cases overall. Now, sometimes referred to as the percentage accuracy in classification. Now, how did I get this number? Because you won't get it in the SmartPLS results. So, how do you get it? This 64.51. So, what is the total number of correct predictions? 61 plus 159 divided by the total number of sample. And you will get 64.51%. Now, in other words, this is the rate of correct classification. Now, if you've got certain predictors and you are trying to predict a particular choice, what is the correct rate of classification? So, the correct rate of classification is 64.51%. Specifically, it presents information on the degree to which the observed outcomes are predicted by your model. Now, the final and the most important thing is the coefficients. Now, what is this? Odds is the ratio of probability. Now, this is your odds ratio. These are your coefficients. Whether these coefficients are significant or not, you get it from your p-value. This is your t statistics or z statistics in this case, which you get by dividing this coefficient by the standard error. Now, the table shows the relationship between the predictors and the outcome. These are all your predictors and whether they are predicting the outcome or not. Now, beta is the predicted change in log odds. For 1 unit change in predictor, there is this much change in the probability of the outcome, which I'm going to explain in the coming slides. Now, the beta coefficients can be negative or positive and have a t-value and significance of the t-value associated with each. Now, this is your t statistic and this is your p-value associated with it. Now, here are our results. Now, what is this? Odds ratio 1. Now, this can be exactly 1 as well. What if this odds ratio is 1? Now, the probability of falling into the target group or selection of private banks is equal to the probability of falling into the non-target group, that is not the private banks, but you can say, let's say, public sector banks. Now, what if this odds ratio is greater than 1, as is this, or this, but these are insignificant. What about this? This is significant. So when the odds ratio is greater than 1, that is probability of event occurring. So the probability of falling into the target group, that is a particular person selecting the private sector bank, is greater to the probability of falling into the non-target group, that is not selecting the private sector bank or selecting the public sector bank. The event is likely to occur. Now, odds ratio less than 1, probability of falling into the target group is less than the probability of falling into the non-target group. So, the probability of falling into the non-target group is higher. The event is unlikely to occur. Now, let's use these results and explain this. Now, value-added services here is 1.373, which is greater than 1. That is, the probability of falling into the target group is greater to the probability of falling into the non-target group. Now, what does this mean? We can say the odds of a customer choosing private bank offering value-added services are 1.373 times higher than those public sector banks which do not offer value-added services. Now, those that offer value-added services have a higher probability of getting those respondents into their fold or to open an account in the private sector banks. By how much times? 1.373 times higher. Now, let's say this was odds ratio greater than 1. What if your odds ratio is less than 1? Now, let's say perceived cost. The odds ratio is less than 1, which means probability of falling into the target group is less to the probability of falling into the non-target group. The odds of choosing private banks over public banks are lower by 0.782 times if the perceived costs are higher for private banks. Now, when you increase the perceived cost for the private banks, the odds of falling into that particular category of private sector banks decreases by how much? 0.782 times. So, look at this negative value. This negative value means that when the perceived costs are high, you do not fall into the target group. Rather, you fall into non-target group. Now, similarly, you can look into this one, the next one, PR. What is PR? Let's have a look. Perceived risk. So, in this case, perceived risk minus 0.509 and it is significant as well, and the odds ratio is less. So, the odds of choosing private banks over public sector banks are 0.601 times lower if the perceived risks are higher for private sector banks. So when you increase the perceived risk, there is lesser chance that people will go for the category or the target group. That is, odds ratio is less than 1. So the probability of falling into the target group is less to the probability of falling into the non-target group. So the people may not choose private banks and they may go for the other types of banks, let's say public sector banks, because the probability or the odds ratio is less than 1. Now here is the reference that you can use to learn more about binary logistic regression. I hope this session would have helped you understand how to use binary logistic regression in SmartPLS. Thank you very much.